Hey there, science fans. Today, let's unravel the mystery behind a workhorse of the electrical world, the three-phase AC induction motor. These motors are everywhere, powering our factories, homes, and even some of our appliances. They are known for their reliability, simplicity, and efficiency. So what exactly is an AC induction motor? Simply put, it's an electric motor that converts electrical energy from a three-phase AC supply into mechanical energy. Unlike other types of motors, these don't require brushes or commutators to operate, making them incredibly durable and low maintenance. The induction part of the name refers to how the motor works, which we'll delve into in a bit. For now, just remember that AC induction motors are all about using magnetic fields to create motion. Pretty neat, right? Let's dive into the core components of this amazing machine. Every three-phase AC induction motor has two main parts, the stator and the rotor. Think of these as the dynamic duo responsible for transforming electricity into motion. The stator is the stationary part of the motor, usually mounted to a frame. It houses coils of wire arranged in a specific pattern. The rotor, on the other hand, is the part that actually spins. It sits inside the stator and is mounted on a shaft. Unlike the stator, the rotor doesn't have any windings in its simplest form. Instead, it's typically made of conductive bars arranged in a cylindrical shape, resembling a squirrel cage. Hence, this type of rotor is often called a squirrel cage rotor. Now, you might be wondering how these two parts work together. Well, that's where the magic of electromagnetism comes in. The secret lies in the interaction between the magnetic fields produced by the starter and the currents induced in the rotor. Here's where things get really interesting. A three-phase AC supply is like the special sauce that makes these motors hum. Unlike regular single-phase power we use at home, three-phase power delivers three alternating currents that are out of sync with each other. These three currents, each slightly offset in time, flow through the stator windings. This creates a rotating magnetic field within the stator. Imagine a magnetic field spinning around like a top. That's what's happening inside the motor. Now, you might be thinking, don't other motors need capacitors to start? And you'd be right, single-phase motors often do. But the beauty of a three-phase system is that the rotating magnetic field eliminates the need for a capacitor to get things moving. The rotating field itself provides the initial push the rotor needs to start spinning. Section 4, the dance of magnetic fields. How the motor spins. All right, we've got our rotating magnetic field, courtesy of the three-phase supply. What happens next? Remember the rotor sitting inside the stator? As the magnetic field from the stator sweeps across the rotor's conductive bars, it induces an electric current in them. This is where Lenz's law comes in. It basically states that an induced current will always oppose the change in magnetic flux that caused it. So the induced current in the rotor creates its own magnetic field that tries to resist the rotating field of the stator. This interaction between the stator's field and the rotor's induced field creates a torque, a rotational force on the rotor. This torque causes the rotor to start spinning, trying to catch up with the rotating magnetic field of the stator. It's like a merry-go-round chase, with the rotor always trying to catch up to the stator's magnetic field. Section 5, the need for slip. Now, you might think the rotor eventually catches up to the stator's field and they spin at the same speed, but here's the catch. It never quite does. The rotor always lags slightly behind the rotating magnetic field. This difference in speed is called slip. Why is there slip? If the rotor were to spin at the same speed as the stator's magnetic field, synchronous speed, there would be no relative motion between them. No relative motion means no induced current, no torque, and the rotor would slow down. The slip is essential for the motor to continue running. It ensures that there's always a relative motion between the rotating magnetic field and the rotor, inducing the current needed to keep it spinning. Section 6, AC induction motors in action. So there you have it. The amazing world of three-phase AC induction motors. These motors are the unsung heroes powering countless applications in our daily lives. You'll find them in industrial machinery. From conveyor belts to pumps, these motors keep factories humming. Household appliances. Many large appliances like refrigerators and washing machines rely on these motors. Electric vehicles. Some electric cars utilize AC induction motors for their efficiency and power. HVAC systems. Fans and compressors in air conditioners and heating systems often use these motors. The next time you encounter a machine powered by electricity, there's a good chance a three-phase AC induction motor is quietly doing its job. They are a testament to the power of electromagnetism and a vital part of our modern world.